नरेंद्र और संजय नहीं है, सो आई विल कंटिन्यू फॉर टुडे। सो हमने रुको एक मिनट स्क्रीन शेयर। सो हमने अभी तक डीपी स्टार्ट किया है, राइट? सो ओके, स्क्रीन दिख रहा है ना? ओके। सो हमने जस्ट कल ही डीपी, कल नहीं मतलब जो मेन, जो मतलब बेसिक प्रॉब्लम बोलते हैं डीपी का, लाइक फिबोनाची नंबर्स और लॉन्गेस्ट पैलिंड्रोमिक सबसीक्वेंस, वो कल कवर किया था। सो आज उसका सिर्फ एक स्टेप अबो है। लाइक आज हम एक क्वेश्चन में 2D डीपी देखेंगे, एक इसमें नॉर्मल डीपी और एक इसमें ग्रीडी प्लस डीपी। सो आज का पहला क्वेश्चन है मैक्सिमल स्क्वायर। लाइक अगर तुमने पहले देखा होगा शीट में, सो मैक्सिमल स्क्वायर है। सो विल स्टार्ट विद दिस वन। So what the question states, first of all, like एक मैट्रिक्स दिया है हमें m by n साइज का. So it's like a it can be a rectangular matrix or a square matrix or or like any other kind of matrix other than which consists of zeros and ones. So only num means if we consider this matrix as nums of I as a 2D matrix, nums of I j. So the elements will have only zeros and ones. So that's like our constraint. And if we see what we need to find out, so we need to find out the largest square containing only ones and return its area. So, like, we need to find out that uh, what how many ones are forming the square, like this one. So this single one is also forming a square. So it will come with the count of one. Let me draw and show you. Okay, so this one is a square. So this one is a square. Now, what is the maximum value here? So here it's 1. Here also it's 1. Here also, if we consider, it will be 1, right? Here also same. Now, if we like move forward in our matrix, so we'll see that we can get only two squares which are of size 2. So like here uh, and this one. These are two squares which we get of size 2. Otherwise, all the squares which are forming are of size 1, as you can see in this particular example. So, what approach we can follow to get our required answer of maximum ones present in the matrix? So, what we can do is uh, we can check the elements of as a brute force. We can check the element of this first element and its diagonal element. So when we are checking the diagonal element, as we need to form a square, so if the diagonal element consists 1 or 0, so then only we'll move forward with our next conditions. So first condition which we will consider is if the diagonal element is 1, then only we'll check for its adjacent element and then check for its uh, previous element. So what we can do here is we can uh, we can apply a brute force approach which traverse whole matrix. So if we see our intuition, so first if we see in brute force approach, it iterates over all possible squares in the matrix to determine the largest one for every cell containing ones. So it considers the top left, top it considers top left, bottom right, and after that all the required elements inside that square. Okay. So if our condition gets fulfilled, we'll move further in the matrix. So here the condition is not getting fulfilled. Here in this square, the condition is not getting fulfilled, so we'll not move to our next diagonal element. So to move to our next diagonal element, we need to have this as 1, right? So what we can check uh, what we can check is, if first we'll assign the values for the size, for the lengths of the matrix, for rows and for columns. Okay, then we'll traverse the row and column simultaneously. So what we are having here is n square complexity of double loops. So once we are entering the loop, we are checking if the required required nums is if the required nums is 1. If it's 1, then only we are proceeding forward, or else we are just staying at the we are just calculating the max and comparing it with the size. So what size we'll see in the loop. So first we are initializing the size with 1. So as the matrix starts with the if it starts with 1, so the minimum size of the largest square containing only ones will be 1, right? So if it starts with 1, so the minimum size will be 1. So now we are considering a Boolean value called valid square. So we are currently setting it true, as we have got a square with size 1. So while moving forward, we are also having a while loop. So what this while loop is doing. So as we can see it here, I plus size greater than row. So it's checking that whether this element and uh, first element plus the size of the matrix which we determined earlier is after adding both those are greater than the rows. Means here the count of the rows is 5, right? So we are checking if we are traversing until the size of the size of the valid square plus the size of the current element is less than 5. And we are also checking the same for the j, which is like for columns, right? And we are checking its valid square. So what this valid square is doing is, right, like we are uh, using it as a flag. So once we encounter a 0, we are changing the we are changing the we are changing the value of the square to 0. So if we see it here, after going through this loop, you will understand that. So if we traverse through this loop, int k is equal to 0, k is less than equal to size and k plus this. So what we are doing it is, we are checking the diagonal element. If it's 0, or the I plus size, if this square is 0, or we are also considering this element. So if any one of this is 0, we are turning our flag to false, and the loop breaks here, and the size doesn't get incremented. So what we can do is, just a minute. If you have any doubt, you can unmute. So to continue forward, uh, if we like traverse in our matrix, If we encounter a 0, we are we are turning our flag into false, and the loop will not move forward after that. Okay, so this condition gets false, so size is not incremented. So after running this loop, we'll see that here, if we consider, wait, if we consider this square, so the size is 1, and if we move forward, the size is still 1. So if we, after considering this square, we are considering this one, the next element towards it. So then we are checking diagonal element to this. If this is 1, we are checking the this above element and the adjacent element. So if these are ones, then we are checking another diagonal element. Okay, so what we are doing it is, we are checking every single possibility, to every single possibility to understand whether we are encountering one at the next stage or not. So this is so here we'll get our max, but we are required to return the maximum count of ones. So if we are traversing, incrementing it from 1 to here, it will be 2, but we'll need to return 4, as all these elements are 1, so the total count become 4. So what we are doing it is, we are returning max into max. This max into max. What this states that, as this forms a square, so if the diagonal element and its above element and its adjacent element are ones, so we are taking it square. To better understand it, like, if this element is this element and this element, we are counting these two elements, right? Once we are incrementing the our size counter, so the count becomes 2, right? After maximizing it, the count becomes 2, but the total number of ones are here are 4. So what we are doing is, we are uh, multiplying the number of ones with the total number of max we have got, so it becomes 4, right? So that we can see it here. So that only we can see it in our output. That's 4, right? So now this is the brute force approach. How we can solve it with like dynamic programming now. Hence, can anyone tell me the complexity of this program, the brute force approach? Quickly, if anyone in the chat box as well. No, it won't be m into n. As we are also traversing in the wait, as we are also traversing after getting the if condition. So we are traversing the whole loop, right? Here we are traversing the whole loop here. So this makes the complexity of n cube, not m into n. As we are traversing through the squares only, right? So if we are like getting, uh, as the constraints are low here, like 300, and the maximum value of n is 300, so this approach would also run with n cube, but to better optimize it, we can use dynamic programming. So how we can use dynamic programming here? So first we'll see, uh, if so in this approach we'll see is, if the encountered element is if the encountered element is 1, so then we are considering the size. We are creating a DP of a 2D DP of matrix, which stores the sizes of further elements. So if we are storing it like here, so it will be 1, right? So now we are considering the minimum of sizes of I minus 1 j, I minus 1 j. So what this element would be if we are if we are keeping the initial value of sizes to 1, so I minus 1 will be 0 and j will be starting with 0. So so this element, what will be the minimum of this? And we are also comparing it with the sizes of j minus 1, j minus 1, this one, and we are also comparing it with this diagonal element. So if this if the addition of this equals to 1, if we are after adding it, if after adding the size of the IFJ is equal to 1, then we are continuing in the loop, or else we are just keeping the sizes of I raised to j to 1. So how we are actually doing it? So first, this is the initialization. So we are first considering a max element, uh, which will check which will check the maximum elements we have reached till. So after entering the row, uh, so here we are initializing the row, and here the columns, the length of the columns. So after this, we are initializing our DP array. So what this DP array stores is, uh, it will have the size of row into columns. So what approach would be optimal is to go by m into n. If you consider this as m and this as n, so that would be your DP size. So how you will be moving forward? So once we are traversing the rows and the columns, if we get the element as 1, if we get the element as 1, we are giving the sizes, we are putting the value of sizes to 1. Hence, if we have encountered 1, so it will set the size to 1. Or else, if we are moving forward, and if we get any other element than 0, so if we are we are considering for 0. So if we get for 1, if we get here 1, so we'll be moving forward. So what condition we had seen it here, it's the same written in here. So if sizes of I comma ij is math.mean, we are also considering the minimum elements of previous arrays which we have got. So if the sizes of I minus 1, I minus 1 j is 0, then we are not moving forward. And if it's j minus 1 is 1, so we are considering the minimum of it, right? So after getting the minimum of it, we are comparing it with our max element. So as we had initialized it with 0, so after comparing, if the max element goes to like 1, max will be 0, and if this is 1, so this will increment the max value to 1, right? As we move forward in this, uh, the rest steps are the same as we had applied in this one. We are checking if this is a valid square. So if it's a valid square, we are just returning the max into max value. Okay. So this it will have a time complexity of n into m. So why? If we are only traversing it once, as we are getting the values of size I minus 1 and the size I minus 1 j and j minus 1 I. So we are getting the values upfront before calculating before going into the loop. So the time complexity reduces here. Okay. So anyone has any doubt here? This can also be further optimized. but we can see it later if we have time. So what will be our next problem is the unique paths too. So this is also an interesting problem. So what we'll be doing is, okay, so this is like a real world problem. So you are given a m into an integer array. Oh, great. This is a robot initially located at top left corner. Means the nums ij is equal to, you can consider it like nums of ij is equal to 0. Means nums of 0, 0 is equal to the robot is initially located at that place. Okay. So when the robot tries to move forward, move to the bottom right corner, that is grid m minus 1 or n minus 1. So like if we see, if it tries to move here or in this square, so the robot can only move either down or right at any point in time. An obstacle and space are marked as 1 or 0 respectively in grid. So here the grid shows whether the obstacle is present or not in the grid. So what this states that only one obstacle is present and it's at the like if we consider the name of the 2D array as nums, so it's at the nums 1 of 1 1, right? So what the question asks forward is, return the number of possible unique paths that the robot can take to reach the bottom right corner. So what we are asked is whether we are able to reach our whether we are able to reach our goal. So this is our goal, and we are starting it from here. So we can only move at, downwards or forward. That's the only thing we can do. So if we move uh, forward, there are no obstacles. So we can successfully move to our next column. Then after this, this one, then this and this. So here we are successfully reaching the goal. So, but we here it's not like if you had seen the unique paths one problem, it specifies that the whether you are able to reach or not to the end goal. But here it specifies by how many unique paths you can get to reach with given obstacles. So here, if we can see is like two paths are there, this one and this one, right? Okay. So how will solve this? So if we see the explanation here, there is one obstacle in the middle of the 3 into 3 grid above. One is right, right, down, down. So it moves to right, right, then down, down. So that's how it moves. And here it's down, down, right, right. So this conditions make it reach to the end goal without encountering the obstacle. So what brute force approach we can use it here? Like we can use uh, like we can check all the possible paths recursively, like this one, then this one. Wait, we can check all the paths like this one, this one here, such that it reaches the end goal. Okay, so we'll also be seeing this one. Yeah, this we have seen already. Okay, so that we can do. Okay, so what brute force we will be doing? So if we see, we are opting for a recursive solution. So what it does is, first it initializes the rows and columns, the length of it, and once we initialize it, we check if there's any obstacle we are encountering uh, in the row which we are moving forward. So if we consider like uh, here obstacle grid, if it's 1 1, so we are canceling that path and returning 0, right? As there are no more rows to move forward. So like if consider like the count of rows is greater than equal to the row. So what we are doing it is we are checking it with the pair of columns. So if any one of this condition uh, falls true, then we are returning 0. And if this condition does not fulfill, we are checking for another condition, that is row is equal to row minus 1 and call is equal to calls minus 1. So what we are doing it is we are traversing with this. We are checking row. If we are initializing row with 1, so we are checking it with minus 1. Then we are moving forward and checking the different column here. And then if the count of the rows finished, we are moving downward with the we are moving downward if to check if there are any obstacle free space. So if there's an empty space, we can move forward, right? And after moving, we are checking if there's any other column in it. If there's any column, then we are moving to that column, or else if there's not no any column, then we are like reaching to our end state, right? Same for this path. This also does the same. So that only we are doing it with the help of recursion. So what we are doing is row plus 1. So we are moving it forward with one space. We are remaining with column with the same column for here changing the row. Then we are checking the count of obstacle grid. So that will be like that will be uh, given already in the question, right? So after moving forward, we'll be adding the rows or the rows and columns which we had traversed, and we'll add the results of both the after traversing the rows and the columns to get our final result. Okay, so this will like return first one, then this will like return first with the one column, sorry, one row, then with one column, right? So that's the thing. Here, it's like 2 by 2 matrix. So here there's only one path. As the right space has an obstacle, so there's only one path is remaining. So that will be our unique path. Okay. So that will be our like brute force approach. So how we can optimize it? So if we can see the constraints, these are constraints are very low, so this would so the brute force approach will also work. But to check for the optimized approach, we can go with the DP. So what we are checking it is the just a minute. So we are checking it is if the number of paths to each cell based on. Am I audible properly? My screen is lagging, so. Just a minute. Okay. So to move forward, we'll check for the DP approach. So what we'll be doing is, what we'll be doing it is, while handling obstacles, will set the path to the cells which are like being our obstacle to zero. So if we like give the obstacle to zero, uh, so the number of DP counts will lower down to zero. So if we see the approach here, so if a cell is an obstacle, so if the cell is an obstacle, the number of paths to that cell is zero. So if we consider like this path, so this path has means the the way to this path, the unique paths becomes zero, right? As there's no chance we can reach our end goal, as there's an obstacle in between. So this one also. So these two paths become zero, right? So after considering this, we are we need will be traversing less amount of columns as compared to our brute force approach. So what we will be doing is we'll not traverse the column of nums of means obstacle grid of uh, 1 comma 1. Okay, so this won't be traversed in our further calculations. So what we'll be doing it is, we'll be moving this way and this way. We'll be moving this way and this way only, and will not be calculating the paths from, if once we encounter an obstacle, we won't be calculating the paths forward to it. Okay, so the paths become zero once we encounter an obstacle. Okay, so we'll see our approach now. So once we set our rows and columns, we'll first check if the start state, if the robot is already at the final state or not. So if it's already at the final state, means we'll not need to traverse any unique paths. So it will be zero, right? As this states. So after this, the condition is obstacle grids rows minus one, calls minus one. So uh, as we are considering the rows and size to starting from one. So once we decrement it, we'll be starting it with zeros. So if the zero is, if the column if the robot column is equal to one, means if traverse successfully, if it did not need to travel through any obstacle, or need not need to travel in any column or any rows, so will return zero, because the robot is standing already at the destination, right? Now what we'll be doing is we'll be initializing our DP array. So what this DP array will look like is, it will consist of values. It will consist of values like it will consist values of like zeros and ones, right? So once we move forward, we'll check if there's any obstacle. So by traversing the rows and columns, if there's an obstacle that is uh, that is one, as this is an obstacle. So we'll consider this path, the paths only to 0. So this will store our unique path. This will consider our unique paths to 0 after traversing through this columns and rows. So once this gets 0, so only need to travel we'll need to travel one less column and one less row, right? In this particular example. So we'll be traversing it with will not be traversing with this column, that is column number 1. We'll be traversing with the rows, with the different rows and different columns, right? So and what we need to what we need to finally attain is the number of counts of unique paths that we are getting it to reach our final destination. So once in the first DP01 we are storing in the first one we are in the first one we are storing the count as 0, right? So at the first robot is at starting position, so the count will be at 0. Then after reaching uh, at the column second and the row first, the unique paths remain for it is only one, that is going to the right. As the downwards, there's an obstacle and we have set it to 0. So we'll not be moving forward with this one. So once we move forward with our next column, then we do not have any other columns to traverse in. So we'll check for the next row to traverse within. So if we are checking for the rows, then we are checking whether there is an obstacle or not. And if there's an obstacle, then we are also turning this path to 0. So this path won't be traversed again, right? So but in this condition, there's an empty space, so we'll be traveling it forward, right? So after this, once we move forward with this one, yeah. So if we can see it in the coding condition. So what we are initializing to our I comma j. So we are checking whether I is greater than 0. So as we have set it here 0, so we are checking if it's greater than 0, then dp of I minus 1 j is 0, or else or plus we are doing it with the we are checking it with the j is greater than 0. These two conditions are important in this dp. So what this states that once we are moving forward, the count to the obstacle becomes 0. So we are just checking for the rows and the columns. If it becomes 0, so we'll not move forward with the same row and column at the same time. We'll move with the like different column and different row which we have encountered the obstacle, which we have not encountered the obstacle with. So here we can see as there are two paths. So what we'll need to return is dp of max. So it will return the dp of rows n minus 1, so, and dp of calls minus 1. So what if we consider it like m and n, so it will like return m minus 1 and n minus 1 until that value. Okay, so that's the question. So if we consider the time complexity of it, the first one was using the recursion, the R brute force approach. So due to those recursive calls, the time complexity had become 2 into n raised to m. If we can see it here, yeah. So this is n and this is m, and we are traversing it. We are recursively traversing it, so it becomes 2 into 2 raised to n into m, right? After using the dynamic programming approach, we are only traversing it once, right? Like not once, we are traversing it twice with each column and each row. Okay, so when we are traversing the row and column, we are checking for the obstacle. And if obstacle is present, we are turning that path into zero. And we are checking that path. If the path is zero, we are not moving with the same column. We are moving with the different column or different row, whether where the obstacle is not found. And we'll be trying to reach our end goal, that is like n minus one and m minus one, right? Okay, so that's for this question. If you have any doubt, you can ask. Okay. You can also ask me if you have any doubt, like after the lecture. So, while you may be practicing it, if you like do not understand anything or any error you get. Okay. So now we'll be moving forward with our third question, that is the jump game. The questions today were covered like in most of the interviews, so we added this in our sheet. So what this question states is that you are given an integer array nums. You are initially positioned at array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. So what we are doing it is, uh, this this is where we stand, right? Nums of zero, and we are checking if the number of counts that we have, that we can jump or not. So this is like the maximum number of count we can jump. So we'll be checking here if we can jump from here to here, here to here to here, and ultimately reaching to our end goal. So we just need to check whether we are able to reach our end goal or not. And if we are able to reach our end goal, we'll return true, or else we'll return false. So uh, what we are doing here is, like in this example, like if we it has two jump steps, right? So if we are moving forward, we can move here. So if we start from here, we can jump to here or directly to here. So the that depends on the uh, depends on the approach what you are using. So if we are if we are traversing to our first, so it gives us three. So after getting three, we can directly reach our end goal, right? So we can say that we can reach end goal here with true. With unlike last example, we do not need to return the unique paths, from here to here, and from here to here, if we are able to traverse all the paths and will be able to reach or not. So what we'll be doing is, if we like jump from one step, so we'll reach at three, right? So after jumping to three steps, we'll reach our end goal. So that makes our condition to true. Okay. So what brute force approach we can apply here is, you can have an attempt to jump at all positions that is mentioned here. So if it's given two, so you will try all possible paths, that is 2 to 3, then 2 to 3 1. So this paths will be covered. So now you will be checking with 3. So 3, you will be reaching to your end goal. And if you consider for 1, so you will be moving forward one step, right? Then again you have encountered 1, so again you can move forward 1. Okay, so if we follow any any number of counts, we are reaching the end goal. But the condition states that only it can be reaching the goal with any number of count. That does not matter. The main intuition is to reach the goal. Okay. So what we can do is we can apply a brute force approach. So what this brute force approach will do is we can uh, we can recursively traverse to each position. So this is the main function, and we are calling our recursive function in it. So what we are doing it is we are uh, returning a boolean recursive function. So what this will be doing is it will start from first element, sorry, from first index till the nums dot length minus one. No, nums dot length means it will traverse until the last element. Okay, so how we can do it like recursively. So first our main base condition should be like if the start is greater than equal to n minus 1. So if this 4 is equal to 2, or the or we are traversing and we are getting the start and the element as equal or greater than, then uh, we can say that we can reach till the end. As consider if it's 4 here, as the first element is 4, and the total size of this array is uh, total array of this 0, 1, 2, 3, 4. So and the total size is 4, right? So if this is equal to or greater than, so 4 steps we can move forward, right? So 1, 1, 2, 3, and 4. So we are ultimately reaching our goal if this count is greater than this count, right? So we'll be comparing this. This will be our base condition to check when to terminate our loop. Okay. So we'll now start to increment the start pointer, that is 2, if we are not reaching the end goal. Okay. So we'll be traversing the whole array once. So what we'll be doing it is we'll be calling this function recursively. So once this function is called recursively with the arguments of start plus I, so this will be like plus this. So it's 5. So it will reach the end goal here only. So it will return true from here, right? But if this count, in the second example, as we can see, if the count keeps on decreasing here, 3, 2, 1, and we have encountered finally 0. So if we see in this example, so if we move forward 3 steps, 1, 2, 3, here will reach till 0, and we cannot move forward to our next step. So if we like go to one step, so 2, so 2 we can go till 2 steps or 1 step, right? So if we go 1 step, then it reaches 1, and ultimately we'll be reaching at this point after after covering all these elements. So what we can conclude from here is once we like reach 0, we cannot move forward in our array. So we'll need to return the false from there on, right? So that only mentions it here. If the if the loop is never if the loop is ne- if the loop is entered, and if the start is if the start is smaller than n minus 1. So if we are reaching it here, and this is n minus 1, right? So this is smaller than n minus 1. So we'll need will not be able to move forward and will need to return false here, right? Okay. So this was the brute force approach. Now, can anyone tell me the time complexity of this? Quick, quick. Recursive calls are made. No, it won't be n square. It will be uh, it will be 2 raised to n. And as we are giving the recursive calls inside the loop to again traverse this path. So this will be called again, right? So this will be like go till 2 raised to n times, right? And as we can see the space complexity, it will be n as we are using the recursion stack. Okay. Now, if we can see the dynamic programming approach. So the dynamic programming approach is not the efficient one here. So as the time is also less, I'm jumping to the greedy approach, like which is new for you as well, and which is quite interesting as well. So what we are doing in this approach is we keep track of the farthest index we can reach. Okay, so here what the farthest index we can reach till 2, right? Then if we move forward, what the farthest index we can reach? It's still here, right? So we are ultimately reaching the goal here. Okay, so that's the greedy approach. So you are not you are considering a criteria and not considering the consequences behind it. So you will be like reaching from uh, three steps forward to it. Okay. Finding the max element in it. So like there are similarities, but you can you cannot say like finding the max element in an array. That's that's quite different. So if like we use finding the max element in an array, we don't know the position of it, right? So if we like get the position of it, so that will determine whether we are able to reach at the last or not. But if we do not know the position of the largest element or max element, will not be able to determine the whether it will be reaching the end or not. Okay, so what we can do it here is what we can do here is uh, so we are initializing farthest to 0. Then we are checking whether the I is greater than farthest. So whether we are checking it, if it's greater than farthest, then return false. Then we are moving forward. Okay. So if farthest math.max, if farthest and the I plus nums of I means the next element towards it is so any max element from it is we are considering as our farthest element. So if the farthest element is greater than equal to nums dot length n minus 1, so if it's greater than this one, then we are returning true. Okay, and once we are returning true, we are getting out of the loop, right? So we are only traversing once in this array, as like we are checking it here, we can reach till here, right? For 2. Then after here we are encountering 1, so we can reach till here, right? Then after encountering 1, we can reach till here. So we have ultimately reached our end. So we'll return the true. Okay. But if we are like in this example, if we are reaching till 2, then after 2, if we are considering 1, then if one path, and then again to till 0, so then after 0 we cannot move forward in our array. So we'll need to stop it here, and the condition will return from here only to return false, right? So this is the greediest approach. Like this can be like solved in uh, big O of n. Like we are traversing the array only once, okay? And we are using here constant space as unlike brute force where we were using the recursion stack. So the will needed a constant space of like n elements, but here we are just using a constant space of 1. Okay, so these are the three questions. uh, Many of the concepts covered in these questions are like asked in real-time interviews, so you can all practice it and give it a try. Yeah, okay. If you have any question, you may ask. Okay. So if there's not any doubt, we can conclude it here. Okay. Thanks for joining.